Hi, my name is Denis Pankratov, and I will be presenting the paper called Graph Exploration by Energy Sharing Mobile Agents. It's a joint work with all these wonderful people that you can see listed on this slide. This is the image of Mars, or a portion of the surface of Mars. And suppose that you drop 3 robots at these different locations. In addition, there are certain points of interest, and there are certain scenic routes that these robots should explore. And essentially, you wish the robots to jointly explore all the routes, because as they go along the route, they see different scenes, they take pictures, they send them back to Earth to be shared on different websites alongside pictures of cats and dogs and things like that. So it's very important to visit every route. Now, the catch is that the robots, they actually have batteries, and the batteries have different charges initially. And the robots can travel a certain distance that is proportional to the battery charge. So, for instance, the robot at the top left corner has very little charge, so perhaps it won't be able to explore too many of these edges. It will explore maybe some of the edges even part way, and then for the edge to be fully explored, the other part of that edge needs to be explored by a different robot. So the question that we're interested in is whether, given this initial configuration of placements of robots, different points of interest and the edges between them and their energies of robots, whether the robots can jointly explore all the edges or not. So mathematically, we model it as follows. We say that we're given an undirected simple graph G, which has a weight function on edges, and the weights, they represent the lengths of the edges. We are also given locations of k agents or robots, which are initially located on some vertices of V. We allow several agents to be located at the same vertex. Also, we know the initial energies of the agents, and travel in length L consumes L units of energy. So energy and distance traveled are in one-to-one correspondence with each other. Now, if energy of a robot becomes 0, then the robot is unable to move. And the question is whether the robots can explore all the edges of the graph G. Now, it's very important to note for the rest of the talk that we're talking about the offline setting, where all this information is known in advance, and the centralized authority is designing different trajectories for the robots. Now, this model is not yet fully specified. There are many different variants of this model we might consider, but of particular importance to us are the 2 variants that depend on whether or not the robots can share energy or not. Can they transfer energy? So in this paper, we focus on the model which allows energy transfer. And this means that if 2 robots are present at the same place and time during their trajectories, then they can choose to transfer a portion or even all of the energy between the 2 of them. So as an example, consider the following simple graph, which is just a path on 4 vertices with all edges having length 1. Suppose that you have robot 1 located at vertex V2, and that robot has initially energy 1 minus epsilon. And there is robot 2 located at the vertex V3 with the energy 3 plus epsilon. Now, it is easy to see that with such an initial configuration, it is impossible to explore the edges of this graph without sharing energy. For instance, robot 2 should be responsible for exploring the edge V3 to V4 because robot 1 cannot reach it. And if robot 2 is responsible for an edge V3 to V4, then it cannot fully explore an edge V2 to V1. And neither can robot 1 fully explore an edge from V2 to V1. So there are many ways of seeing this, but essentially that's one of them. But if you allow the robots to transfer energy, then you can explore this path as follows. Robot 2 starts out by going from V3 to V4, then it turns around and travels all the way to V2. In this part, the robot spends 3 units of energy. At this point, epsilon energy is transferred from robot 2 to robot 1, So now robot 1 has energy exactly 1, which is enough for robot 1 to finish exploring the edge of the graph. So this already highlights that this capability of sharing energy is actually quite important, because sometimes it allows exploring certain topologies which are not explorable without energy sharing, but with other conditions being equal. And our work can be viewed as a step in this direction of understanding this energy sharing capability. So we focus on energy sharing, but also we compare when certain things are achievable with energy sharing and contrast it with similar situations when they're not achieved with energy sharing. This question can be further explored, and it is quite of interest. Okay, so our main results with energy sharing, we show that for paths of length n, there is an order n plus k algorithm that finds exploration strategy if one exists. So recall that k refers to the number of agents. In another result, we show that for n-node trees, there is also an efficient algorithm, but its time complexity is n plus lk squared, where L is the number of leaves in the tree. Our other result is to show that it is NP hard to determine if an exploration strategy exists or not in 3 regular graphs. And so this paints a picture that the problem is easy for trees, but then as you increase the graph class to include 3 regular graphs, then the complexity of the problem jumps up. Now, there are other results in the paper which I will not be discussing with great details, but they are of interest. So some additional results are that we show for a path graph, if total energy of all agents in the system is at least 3/2 times the weight of edges, then the path can be explored. So recall that not all initial configurations allow for exploration of a graph, but if there is sufficient amount of energy for a path graph, then it is explorable. And for general graphs, a similar statement also holds, but here we require that total energy of all agents in the system is at least 2 times the total weight of edges. And then the graph can be explored. Okay, so let's now discuss some related work. And I should say that it will be a rather short discussion because exploration and search problem literature is rather vast. There has been over 50 years of research, so if I try to do it any justice and try to explain what has been done, I would spend all the rest of the time for this presentation. There are hundreds of papers even for the line topology. But in terms of energy-related works, so on models where you have agents with the energies traveling distance proportional to the stored energy, these works are a bit more recent. So it has been shown that different tasks such as data delivery is NP hard, even on simple topologies when either there is no energy sharing, and even when networks, when mobile robots have certain restricted capabilities, such as carrying capacity or so-called low power mode of robots. Now, there has been a sequence of papers by Shizovich et al. That consider energy sharing model. And they studied several different tasks and have provided some efficient algorithms for restricted topologies, such as, and the tasks include data delivery task, converge cast, broadcast, and there are, of course, other related models that have been studied, such as an online setting, where there is wireless communication between robots, but there is no centralized authority and the graph is not known in advance. And as you can see, a lot of these topics, they have been explored at previous Sirocco conferences. So this paper that I'm presenting continues this well-established tradition. Okay, so next in the talk, I'm going to discuss our algorithm which allows efficient tree exploration. But before discussing it, I would like to quickly note that without energy sharing, the problem is NP hard, even on star graphs. So this goes under this theme of comparing what is possible with and without energy sharing. So there is a reduction from the partition problem that has been known since at least 2006 for this setting. So recall that in the partition problem, you're given positive numbers a1 to an, and let's define capital T to be half of the summation of these numbers. And the question is whether there exists a subset of these numbers that adds up to this T. So whether you can partition the numbers into two blocks of equal sum. So the reduction goes like this. You construct the star shown on the left. You have a single center node, center of the star, which has leaves v1 to vn. And leaf vi is connected to a center c by an edge of weight ai over 2. And then the center c is connected to two special nodes s1 and s2 by edges of weight t2, 2t each. And you place two agents at the center node C, and each agent has energy 3t. Now, it is easy to see that the two agents can jointly explore the star if and only if they among themselves can partition which agent is responsible for visiting which VI. Visiting a particular VI incurs a cost of AI over AI, because it's AI over 2 in one direction and AI over 2 in another direction. So if they can perfectly balance the leaves so that the exploration cost is T for each of them, then they can visit the corresponding leaves and then go to S1 or S2 and complete the whole exploration with 3T. And if they cannot partition which agent is responsible for which leaves, then they cannot visit all the edges. So this reduction shows that without energy sharing, exploring even such simple trees as stars is NP hard. Okay, but we show that with the energy sharing, we can solve trees quite efficiently. So this theorem is what we're going to discuss next. And we establish this theorem in 3 steps. In step 1, we do some preprocessing. We convert the input tree into an equivalent rooted full binary tree where all the agents are located at the leaves. In step 2, we solve this rooted full binary tree case using 2 dynamic programming arrays computed in parallel. And in step 3, one can extract the exploration strategy, if it exists, for the original input from the solution for the full binary tree. Now, step 3 is left as an exercise to the viewer, but I will discuss step 1 and step 2 with some details next. So for preprocessing, we do it in several sub-steps. So suppose that this is the input tree that is given to us, and in red I indicate locations of agents initially. So as a first sub-step, we push all the robots into newly created leaves. So we create, for all robots that are not already at the leaves, we pop off a new node connected by an edge of weight 0, and we relocate the robot from its original position to a new leaf, like this. Clearly, the exploration, if it existed in the original tree, it also exists here, and one can efficiently convert back and forth. And it will hold true for all the sub-steps that I discuss next. Okay, next we consider vertices that have degree more than 3. So here there are 2 such vertices that are highlighted in green, and the degree of these vertices can be reduced by creating new vertices and introducing some edges of degree 0. That way we split the degree of the original vertex and accumulate it as in terms of different degrees of newly created vertices. So here we do it like this. After this, we find any vertices of degree 2 that we have in the graph. Here it is again highlighted in green, and we're going to contract them, meaning that we're going to remove this vertex, and since it has 2 edges 7 and 3 incident on it, we replace the 2 vertices connected by this path by a single edge. We connect them by a single edge of weight 10. So now we have this tree where each vertex has degree 3 or degree 1. So then we pick an arbitrary edge, highlighted in green here, we split it in the middle by inserting a new vertex, and we designate this new vertex to be a root, and then we root the tree. So this way we get exactly a full binary tree where all agents appear as the leaves. So now we're going to assume that this is the input, and we need to solve the problem for these types of input. This is going to be handled by a dynamic program that we designed for rooted full binary trees. And for that, we're going to consider different vertices V in the tree. So we denote by T sub V the subtree rooted at the vertex V. And in the subtree, there may be some agents at the leaves. And we define the following dynamic programming table, which we denote by BVI, which is going to store the maximum possible surplus energy that can leave this subtree after it is fully explored, and I agents can leave with this total energy. So intuitively, just by considering this problem, if we want to explore all the edges, during this exploration, the energy may be shared, it may be transferred, it can come into this subtree TV, it can leave this subtree, as well as the agents, maybe 3 agents that are shown here that are in the subtree TV are not enough to actually explore the subtree and finish exploring the whole tree after that. So you might need to bring in more agents, or maybe these agents need to leave the subtree. So this indicates that we need to keep track of essentially 2 key elements. One is the balance of energy that is going into the subtree TV or leaving the subtree TV, as well as balance of agents. We store balance of agents as an index into the table. And the balance of energy, the optimal balance of energy for this subtask is stored in the table itself. So it's important that I here refers to the balance of agents, so it could be negative. And I being negative means that some agents need to come into this tree. BVI could also be negative, which indicates that some energy is needed to finish exploring this subtree. So there are some important notes that if the balance of agents is negative but balance of energy is positive, it means that some agent must leave the tree to carry the extra balance of energy out of it, but overall more agents need to come into the tree. And the second point, which is important and leads to the next dynamic programming table, is that this BVI entry, it doesn't incorporate the energy needed to explore an edge between V and its parent. And the energy needed to explore these edges are actually important if you try to go ahead and compute these BVI entries dynamically. And lastly, we know that for a node V, the balance of agents that we need to consider, so the indices I, go from minus k plus AV to AV, where AV is the number of robots initially present in TV. Okay, so as I mentioned, if you wish to compute B for vertices, you actually need to do something with the edges, and we handle it by extending the definition of B to the edges. So if you have an edge from U to V, and this edge is labeled E, then BEI stores maximum possible surplus energy that's available at vertex U along the edge UV, if the balance of agents that could transit from from V to U is I. And this is a bit of a mouthful, and maybe English description is not quite clear, but especially in light of I possibly being negative. If I is negative, then it refers to the surplus of energy that can be made available at U if some number of agents travel from U to V. But agents might also get stuck along the edge from U to V. Maybe we abandon an agent that runs out of energy. So all these things, they complicate the calculation of this, and perhaps the best way to understand what is happening in the calculation of the arrays B, EI, and BVI is to follow along in the paper for different cases of the computation, and they would eliminate the interaction between these two arrays. Now, the way that they are computed, these two tables, they are computed concurrently in a bottom-up manner, starting from the leaves and proceeding up the tree towards the root. And a vertex array is actually easy to handle provided that you have an edge array. In particular, BVI, if V is a leaf, we simply record in it the total energy of all agents present at V for the allowable values of I. And if V is not a leaf, it has two child edges, E prime and E double prime. And what we need to do, we need to decide how to partition this balance of I agents, balance of agents at V, into I prime and I double prime, two different balances for the corresponding child edges. And we just find which partitioning of the balance I gives us the maximum value for B of the corresponding two edges. To compute BEI, as I mentioned, the robots spend energy traversing the edge itself. They can stop in the middle of an edge, and this makes it a bit more involved. So there are many different cases that we need to consider, but it is possible to do. And you can see the details of the paper in the paper. Now, at the end, if V is the root, then we check, does there exist a BVI value which is non-negative with non-negative balance of agents I? If there is such I, then we return solvable, and otherwise we return not solvable. And one can use these arrays and the way that they are processed to extract the actual trajectories for the agents. So this theorem is established this way. Now, I would like to make a few more comments, and in particular about the theorem for general graphs. We can show the total energy of all agents, if it is at least 2 times the total weight, then the graph can be explored. And this is established by the following steps. So first we start by doubling edges of the graph to get an Eulerian graph G'. Then, because G' is Eulerian, we can construct a cycle C that visits every edge exactly once. And then we can apply the well-known algorithm to explore a cycle. So that's a high-level overview. Now, for the theorem which gives an efficient algorithm for paths of length n to find an exploration strategy if one exists, this is achieved by a greedy algorithm. That algorithm, and proving its correctness, is non-trivial, and it illuminates interesting properties of different trajectories of the agents for the path. And to establish the NP hardness in case of 3 regular graphs, we use a gadget reduction from Hamiltonian cycle. The proof is not straightforward. Here is an example of the gadgets. They look kind of like these whiskers. And lengths A and B need to be chosen carefully, and the initial energy values assigned to robots need to be chosen carefully to ensure that an optimal strategy, if one exists, would correspond to a single cycle in the graph, as opposed to multiple different cycles. Okay, so lastly, I would like to mention some open problems regarding graph exploration and energy sharing robots. We have considered the question of whether it is possible or not to explore the graph with given energies. But of interest also is an optimization version, where we are trying to optimize total energy consumption. We can also talk about agents with a limited battery capacity so that they cannot just share arbitrary amounts of energy between themselves. A question arises, what if positions of agents are not given to you, but you're free to place agents somewhere in the graph? Can you find the placement of agents and maybe distribution of energies that is going to give energy optimal exploration of the graph? Time versus energy trade-offs for agents with different speeds might also be important and interesting. And of course, exploring additional topologies of graphs is a natural and interesting question. So I thank you for listening to this presentation. And if during the literature overview I forgot to mention some important work, please forgive me. And thank you.